Okay, today we're doing analysis. Now, analysis is not an examined part of the course because, truthfully, it's not on the syllabus, but we put it in because you will need it in order to do the job. So it's in there because it's something you're going to need. Sort of things that instrumentation deals with analysis is measurement of various things. pH, conductivity, oxygen, dissolved oxygen, nitrogen, chlorine, carbon monoxide, carbon dioxide, turbidity, and colour. Now, have any of you ever seen any or worked on any of these type of analyzers or instruments? pH, okay. Anybody else? No, fair enough. We will go through them then. O2, okay. Right, the first one we'll look at is the pH sensor. Now, why do we measure pH? We measure pH because it's one of the things that is important to us. Basically, getting pH correct means that we have the material correct. The equipment is protected. But mostly the reason we measure pH is because we have to, because it's legislated. What does pH mean? pH is the measure of the negative logarithm of the free hydrogen ions. Does that mean anything to anybody? Well, I tell you what, it means absolutely nothing to me. So, pH is this funny number. What pH actually means is, it's a number. It's a number from 0 to 14. In the middle, at 7, is what's called neutral. In the middle, at 7, is water. The further away you get from 7, the more it will burn you. So the more burny it is. So if we look at pH, if we start at this end, at the 0 end, 0 is far away from 7. So at 0 up to 7 are the acids. The further away you are from 7, the more it burns. So 0 is a long way from 7, and we have H2SO4, which is sulfuric acid. That's battery acid. Battery acid, as you know, burns. Or anybody who's had to deal with, well, you're an electrician, so you know that. And then we move a little way along into HCl, hydrochloric acid. Hydrochloric acid is one of the main constituents of stomach acid. See, when meat arrives in your stomach, the stomach throws acid at it to dissolve it. And it's very good at dissolving meat. And then moving along to the 2, and just beyond 2, lemon juice. Lemon juice, orange juice, lime juice, they're citric fruits. They contain citric acid. Acetic acid, or vinegar as we call it. Beer, slightly acidic. Cheese is acidic because cheese is made from milk, and milk contains acid. It's called lactic acid. Lactic just means milk, so lactic acid is milk acid. It's only very slightly acidic because it's only just slightly away from 7. Once again, the rule is the further you are from 7, the more it will burn if you drop it on your hand. 7 is water. Water doesn't burn. Now, when we go up in numbers from 7, we go into the alkali region. Sometimes that's called bases. So we go into the alkali regions. Alkalis and acids, they're like enemies. They're like cats and dogs. So going down into the alkali region, the first thing we bump into is egg white, slightly alkali. Sodium bicarbonate is alkali. Strange enough, in your stomach, the stomach throws acid at things to dissolve them, and then in the next part of your gut, which is called the duodenum, what they do is they throw sodium bicarbonate at it. Because what happens when an acid and an alkaline meet is that they neutralize each other. They form gases, and they form salt plus water. Acid plus alkaline forms salt plus water, which is one of the reasons why the oceans are so full of salt plus water. Going further into the alkalines, we get potassium acetate, that's acetate, milk and magnesia, drain cleaner, calcium carbonate, or chalk as it's often called, lime, this is lime as in limestone rather than lime as in lime juice, and sodium hydroxide. I can't remember what that's called. Drain unblocker. No, what is it? No, I can't remember the name of it. But these are all the alkalis or the bases. The rule still applies. The further you are from 7, the more it will burn you. Caustic soda, that's what that's called, caustic soda. So the further you are from 7, the more it burns, either going up towards the acid end or going down towards the alkali end. Now, whenever an acid and an alkali meet, there's lots of fizzing, lots of bubbling, possibly explosions, and they neutralize each other to form salt plus water. To measure pH. Firstly, to measure pH, what sort of stuff do you put in batteries? Well, put another way, what have you got in your car battery? Yep, that's right, you put an acid. What other type of batteries are there? There are acid batteries. What other type of batteries are there? What are Duracell batteries made of? G'day, Eddie. What are Duracell batteries made of? Lithium. Yeah, lithium. But the liquid inside batteries. Lithium is the metal. Alkaline. Funny thing about acids and alkaline. The more acidic something is, or the more alkaline something is, the better it acts as a battery. See, a battery is basically a couple of bits of metal with either an acid or an alkaline in between them. So, and the stronger the acid or the stronger the alkaline, the more volts it creates. So if you took your car battery out and you tipped all the acid out of the car battery out and you filled it up with water, it would still be a battery, just not a very good one. It wouldn't produce very many volts. If you then filled your car battery up with a strong alkaline substance, it would make volts. But it would make volts in the opposite direction. The polarity would change. So if you want to know what pH a substance is, all you have to do is stick it in a battery and see how many volts it creates. The more acid it is, the more positive volts it will create. So that hydrochloric acid, battery acid as we call it, sulfuric acid, produces lots of positive volts. Whereas a very alkaline substance would produce lots of negative volts. So to all intents and purposes, a pH probe is simply a couple of metal plates. There's a few little odd wrinkles, like the fact that the ability of a battery to produce voltage is very dependent on temperature. So we tend to have a reference probe as well to counteract the temperature effects. But to all intents and purposes, what we've got is a metal plate, maybe two metal plates, and we simply measure the amount of volts it produces. The more volts it produces, the more acidy or alkaline it is. The polarity, that tells us whether it's acid or alkaline. So you have these different types of electrode. Now, we don't actually want the little thin piece of metal, which is inside the electrode, to come into contact with the acid. So what we have instead is we enclose it inside a very special piece of glass. And this piece of glass is ion permeable. What that means is the the hydrogen ions, the bit that makes something acidy or alkaline, are able to pass through this glass and get to the electrode. Now that gives us all kinds of problems. The kind of problems it gives us is that this glass is specially made. This glass has got a limited shelf life. From the moment the pH probe is made, it starts to go bad. It has a limited shelf life, and the older it gets, the more useless it becomes. So that's the first thing to bear in mind. Second thing to bear in mind is it's glass. Glass is very, very fragile. There was a German chap called Nernst who came up with an equation that stated that if the voltage output from a probe will be basically a straight line in relation to its pH. So that's nice. What that tells us, if we want to calibrate a pH probe, we only really have to calibrate it at 2 points, or at best 3. When you are calibrating pH probes, what you have to do is you give it 3 different solutions of different pHs, and you press the calibrate button, and the thing just sort of calibrates itself. Okay, how's that the sound, Eddie? Is that too loud? Hello, Eddie, I'm testing sound. Or has it gone all squirrely again? Sometimes the sound on this thing goes a bit like I'm being, taking helium. Okay, good. We'll carry on. Now, calibration of pH probes. How frequently should the electrode be calibrated? Before we get into this, what I need to tell you is the pH probe was designed for use in a lab. It was for use in a lab where you'd get a little lab technician wearing a white coat who would love it and tend it and look after it and clean it and calibrate it every day. It was never ever designed to be used in the field. It is not rugged enough to be used on a mine site or an oil rig or in the field. But unfortunately, legislation came along and said we have to test the pH. So we had to put these lab sensors in the field. Now, what we have now is basically a lab sensor which we've mounted in the field. I'm trying to find a polite way of telling you that it's a complete piece of rubbish. It's a dreadful, dreadful sensor. All pH sensors. Some are better than others, but basically they are all rubbish. From the moment the probe is made, it starts to deteriorate. It has a limited shelf life, and the older the glass gets, the more it drifts out of calibration. Basically, how frequently should it be calibrated? It depends. It depends on how accurate you want the results. If you want a truly accurate pH reading, you need to do a calibration and take the reading there and then. Within half an hour, you can't honestly trust the pH sensor. The older the probe is, the more often you're going to need to calibrate, because the older the probe is, the quicker it goes out of calibration. Those of you that have dealt with pH probes know that basically a pH probe is a nightmare. You need to calibrate it, well, once a day, probably. At least once every 3 days. If you can get away with once a week, then you're lucky. So a pH probe is just a constant battle to keep the thing in service. You can't even keep a spare in the cupboard, because the whole time it's sitting on the shelf in the cupboard, it's losing its ability, it's going off. So if you buy 2 pH probes, you mount one of them and you stick the other one in the cupboard, by the time the first one's stuffed, so's the second one. You actually have to order the spare to arrive on site when you need the next one. They're completely rubbish. And like I say, the only reason we use them is because of legislation. If you actually want a decent pH reading, you should really use just a bit of litmus paper or something like that that gives you a decent, proper, accurate reading. If you have the pH probe mounted anywhere where the water or the liquid might be dirty, then that can poison the glass and damage it even further. So they're very, very sensitive. They're very sensitive to all sorts of stuff, and you really should calibrate it all the time. They're sensitive to temperature. Temperature does influence them. It changes the slope of the equation. So they need to have a good temperature sensor attached to them to calibrate for temperature. This is the way temperature changes the Nernst equation. It changes the slope. And it changes the slope a lot. I mean, a lot. You know, there's a lot of error can be brought in by a mistake in temperature.